computer. Thank you very much. And let's share the screen again. Oh. Okay, so it's an invisible entity, and we visualize it by representing it as an arrow, which is the representation of a vector, right? And the first electric field that we covered was the electric field of a point charge. Okay, that's the first one we cover. And let me go here to my notes, and I wrote down, right, the equation for the electric field of a point charge. Here you go. That's the electric field of a point charge Q1. Okay, like in vector format. In vector, remember that. And we also covered the electric field of a parallel plate, uniformly charged. Okay. Write that down here. We covered, seems supposed to be insert, page break. We covered the E field of a point charge. Point charge. And it's very similar to Coulomb's law. The only difference that we do not have a second charge there in the equation. So the expression is like that. E Q1, that's the electric field of charge 1, right? And I'm going to simplify the notation. Just put R squared, which is the distance from the center of the charge. Point charge, okay? And we also covered the electric field, the field of two parallel plates uniformly charged. Okay, and it's a constant, the constant vector. Okay, for the space in between the two plates. That's what you have to know. Okay. And I also showed you an illustration, and I'm going to get this illustration for you. Electric field. Let's see here. Okay, here you go. Here's the electric field of a point charge. That's how we illustrate the electric field of a point charge in a vectorial sense, right? The closer the field is to the charge, the stronger it is. The further away it goes, the length of the arrow decreases. But there is another representation that is the electric field lines. And the strength of the electric field is, and by the way, the electric field is going to be tangent to those lines, okay? Tangent to those lines. And the strength of the electric field is dictated by the density of electric field lines in a given region. The density of electric field lines here is greater than the density here. Consequently, the electric field here is stronger than the electric field here. That's for the point charge, positive point charge, negative point charge, right? And then we solved some problems, right? We want to know, for instance, the electric field configuration of different electric charges. And for instance, for 2-point charges. And we go ahead sum those vectors. And this one is another example. That's a dipole. One is a positive charge, the other is a negative charge. Okay. Just a quick review, right? What we we have been doing. And then this is another type. Let's see, this one is a quadrupole. I'm not going to cover that because now it start to become more complicated. Okay, so let's close this one. And then what else we're covering? We covered the electric field of a continuous distribution of charges. There's the electric field of a point charge distribution. There's the electric field of continuous distribution of charge. The parallel plate, for instance, is a continuous distribution of charge. And it's one of the most important ones because it results in a uniform electric field. You saw right in here. Whether it's a single planar distribution of charges or two planar distribution of charges, the field is going to be uniform. If you have a single positive planar charge distribution, the field is going to be uniform on the right side and uniform on the left side. Then that's how we represent a uniform field, right? Those vectors, they are all pointing the same direction. Not only they are pointing the same direction, but their lengths, their strengths are the same. That's for a positive plate. For a negative plate, those fields are going to point towards the plate. And I'm going to emphasize that this plate here is negative. I'm going to replace everything here by the negative sign. Okay, so there is no doubt this is a negative distribution of charge. But in practice, we don't use just a single planar charge distribution. In practice, we combine those two positive and negative planar charge distribution, okay, like that. And when we combine them, all the field outside the volume between the plates is going to end up zero, okay? And we do that, we find that out easily just by using the superposition principle. Okay, we do know that the electric field of the blue plate or positive plate is going to be given by those blue vectors, pointing to the left and pointing to the right, right? So what you have here is this figure here combined with this other figure here. It's very simple, okay? All you have to do is
because I was like, I don't know if you noticed, but I was like,
let's
yeah,
see.
I was like, where is she?
Okay, someone forgot to turn off their mic, right? So here you go. All I'm doing that in that problem is to combine this vector configuration with this other vector configuration. When we combine them, inside the volume, the field of the right plate reinforces the field of the left plate. But outside this volume, this region, all those fields, they cancel each other. Okay, so that's what you have to know. A constant for the space between the plates. And E equal to 0 elsewhere. E equal to 0 elsewhere. Okay, insert. And how do we represent this electric field in terms of electric field lines? Okay, the same way that we did before. So let's see if I can have a drawing here. Yeah, I'll have to draw from scratch. Okay, so I will use what I already have here. Here you go. That's the net field. I'm going to erase all those. You know what? I don't need to erase. All I have to do is get one of those vectors and stretch it like that. But before, let's remove. Yeah, ideally we have to remove it. Good. This one? No. Yeah, I'll have to remove one by one. And then all I have to do is to stretch my vector lines from the right to the left. Ay. There must be an easier way to select this thing, but it doesn't let me do it. So I have to do that one by one, unfortunately. Like that. Ah, man, I hate that. Instead of erase, it's duplicated. Erase it? Good. 1, 2, 3, 4, 5, 6, 7. Okay, there might be an easier way of doing that. For some reason, let's see if I do something like that. Yeah, I erased all that completely. I don't want that. So now I'm going to stretch my vector. That's my electric field line. The spacing between the arrows must remain the same if you want to represent a uniform electric field. And I want to view the grid lines to make sure my vectors are straight. Yeah, they are straight. One more. This one I don't need it. Erase it. One more. One more. And so on. All right. Huh. Oh, stretch. Let's see if I can copy all of those simultaneously and paste in there. And now I paste it. Here you go. And then save me time doing that, right? Go. Okay, so that's a representation of a uniform electric field. Let's see what we have in your book as well. So here you go, electric fields. More students coming in. Electric field of a point charge. Here he's calculating the electric field, an example of an electric field of a point charge at a given distance. And what else do you have to know? You have to know because, Shigo, there's a very important result for the electric field as well. Okay, and I'm going to spell that out for you. Let a charge one with a given electric field, right? You already know. Let a charge Q1. Let a charge Q1 with a given electric field. You already know that the mathematical equation of the E field of this charge is. And I'm going to emphasize that the electric field of charge 1 by putting a subscript 1, K Q1 over R squared, like that. Now we introduce another charge Q2 nearby Q1, okay? What is the electric force applied on this new charge, okay? So there is a very important, I'm going to put here solution. There is a very important relationship between the electric field and the electric force. What you have to know is that for any charge distribution, right? The electric field of a given charge is going to be the force that exists between the regular charge and another one. So the force divided by the second electric charge is going to be given by the electric field. Okay? And so if you want to find out the force between those two charges, all you have to do is to multiply the new charge by the original electric field. Okay, remember that? That comes from the very definition of electric field. Going back to the book. Okay. More students coming. Here you go. That's a complicated distribution of electric field, the electric charge. Right? Here you go. There's the parallel plate. The parallel plate capacitor. There is a device called a capacitor that we are going to introduce to you later on, okay? The capacitor, the parallel plate capacitor is just what the name says. It's a device that you have two parallel plates, one positively charged and the other negatively charged. The magnitude of the charges in each plate is the same. And we get this uniform electric field between those two plates. They sell this type of device out there in the market. We use them in electrical circuits, electric and electronic circuits. Okay. Electric field lines, here you go. For a point charge, here you go. That's how it looks like the electric field lines for a parallel plate. And you're going to get something like that in the lab that we're doing, okay? If the plates are infinitely long, they are all the lines are going to be uniform like that. But if the plates, has a dimension, a given dimension, a finite dimension, something start happening here at the edge of those plates. Okay, the field start to deviate a little bit more, and that can be explained rather easily in terms of the charges that you have here. Okay. I'm going to explain that to you. And I want you to practice this explanation, so you can have a good way of visualizing those electric fields, okay? So here you go. I'm going to do the following. I'm going to use, I'm going to use this guy here. Let us see what happens at the edge of this plate, right? First, let's work this use this parallel plate only. And I'm going to shrink it a little bit so you can have a better idea. Okay, we have enough space here. Okay, first, I'm going to find out in a rather qualitative way what is the electric field. I'm going to remove those vectors, okay? So you can understand why we have that deviation from a uniform field at the edge, okay? So if you're going to find out suppose that you want to find out the electric field right here at this spot, okay? And I'm going to put a spot in there. Nope, this one. Suppose you want to find out the electric field right in here at this spot. What's the procedure, right, that we use? Okay, what we're going to do, we are going to find out what's the contribution of this charge, okay? The contribution here of this charge is going to be something like that. Do you agree? Okay, at the very edge. That's a very qualitative way of calculating the field, but it's very useful too, okay? And then we find out the contribution of the second charge that is right in here. And we go ahead, do exactly the same thing that you did before. Draw a straight line from the charge to this point right here. And you can see that this electric field deviates a little bit in the direction, okay? Not only deviate a little bit in this direction, its magnitude is going to be slightly greater than the other because this charge here is closer to this point than this point here, okay? And then you do for every little piece of this charge distribution. Let's figure out what's going to be the charge contribution, the field contribution of this other charge, right? That's getting closer and closer to the center of the plate. Here you go. It's going to be something like that. The magnitude of this field must be greater than the other two because the charge is closer to the point, and but the field deviates a little bit more. And then finally we get this charge here at the very middle. It's going to have a contribution to this electric field that was something like that. And then we repeat for the other half. Okay, we did for this lower half, we repeat that for the other half. Because the amount of charge that we have here is exactly the same as the amount of charge that we have here. It means that we are going to have a mirror image of the electric field contributions in this direction, okay? And what I'm going to do, I'm going to copy those fields here, paste. I'm going to group all of them, and then I'm going to do something else. I'm going to produce, instead of doing one field after another field, I just come up with a simpler way, easier, right, of doing that. And I'm going to do the following. I'm going to group this one as well, so I have a very good reference. Okay, and then what I'm going to do, I'm going to produce a mirror image of those fields that you see right in here, something like that. If I did everything right. Okay, yeah. It looks like I did. What's going to happen? You're going to have a net field at this point that's going to be pointing only along the horizontal direction. Okay, here you go. Do you agree with that? So in the very middle of the field, you can see that the field is going to point the horizontal direction. As we move away from the center of the plate, what's going to happen? Suppose now what? Suppose that I want to calculate to find out the field, not here at the middle of the plate, but the field here at the edge of the plate. Something else is going to happen. Something else is going to happen. Okay, so I'm going to have a field contribution by this electric charge here. Okay, and because this one is the closest one, the field is going to be the strongest one. Let me make a little bit longer. And then we are going to have a field contribution from this other point here. And now you can see why the field deviates from the horizontal direction at the edge of the plate. See that? Overall, okay? Overall, what's going to happen? That's what we call the edge effects of the charge. Overall, we're going to have more or less an electric field that's going to be in this direction. Okay? And that's why the book illustrates an electric field that deviates from a uniform field right in here at the edges. Okay? And that's the type of thing that you're going to see also in our lab. But in general, the field will be uniform right in here in the bulk, and it's going to be just slightly deviated at the edges of the plate. Okay, I'm going to write that down for you. To first order approximation. Okay, here you go. To first order approximation, comma, an electric field the electric field of an uniform planar charge distribution. So first order approximation will be uniform. Uniform planar charge distribution results in a uniform electric field. In other words, a uniform planar charge distribution generates a uniform field. Okay? Uniform charge distribution. Charge distribution means that you have the same concentration or density, right, of electric charges throughout the whole plane, throughout the whole plane. Okay, that's what uniform charge distribution means. However, strictly speaking, at points nearby the edge of the plate, the field will deviate slightly from that of a uniform field. But remember, only in the points nearby the edge of the plate, okay? Only the points nearby the edge of the plate. It's going to be something like that. This field, I'm going to make it a little bit more. Yeah, it's going to be something like that, okay? Here nearby the bulk, you're going to have something like that. A little bit further away. And now it's as we get closer and closer to the edge, then the direction of the field start to deviate a little bit, okay? I'm just exaggerating here, okay? But again, to first order approximation, you should expect the electric field to be uniform throughout this whole space. And just like before, I'm going to come up with a mirror image of those fields. Here you go. Right, and like that. Like that, okay? Edge effects, we're going to write that down, right? Don't forget. So there are some edge effects at the edge of a planar charge distribution. Insert page break. Okay, so let's see if we have anything else more. Here is the field distribution for a dipole charge distribution. Okay, it becomes rather complicated, the field lines, when we get one, two, three, when we get two or more point charges, right? Distribution. Two positive charges, that's how the field lines look like. And then we have this, what we call the quadrupole. Quadrupole, let's say one. No, that's a different dipole. That's a different dipole, okay? Now we're going to skip electrophoresis of DNA. We are going to skip electric field inside a conductor. And then we have Gauss's law. Now, what's Gauss's law? Gauss's law. Gauss's law is just another way of expressing Coulomb's law. Coulomb's law. Okay? And it is also a more convenient way of calculating the electric field of a given charge distribution. That's what Gauss's law is all about. It's another way of expressing Coulomb's law, but it also is a more convenient way of calculating the electric field of a given charge distribution. And I'm going to formulate that for you. I want you to learn that. Gauss's law. Okay. Before we get into Gauss's law, we have to define something else that we call the electric field flux. Okay. Electric flux, even better, electric flux. Okay, the electric flux is a very important concept. Flux is a measure of how many electric field lines goes through a surface in the 3D space. Okay? Remember, it's a surface. And let's see. Let me see if I have a good illustration for that. Gauss's law right in here. Okay, so here you go. Suppose, for instance, that you have, here you go, here's an illustration of Gauss's law and the concept of the electric flux. Okay, Gauss's law uses this concept of electric flux through an open surface in the three-dimensional space. So I'm going to illustrate that. Suppose that we have these electric field lines here in space, uniform electric field lines. Okay, we don't need this guy. Yeah, we don't need this guy yet. And what I'm going to do, I'm going to create a arbitrary, imaginary, even better, an imaginary planar surface that is perpendicular to those electric field lines. Can you picture that? Okay, so here you go. I'm gonna illustrate here in my own three-dimensional space. I'm gonna stop sharing so you can see that. So suppose that we have this electric field right here. My pencil is an electric field. Let me stop. Yeah, here you go. So this pencil here illustrates an electric field in space. Let's say we have, if you have a uniform electric field here in my space, my three-dimensional space, it means that there will be an arrow here in this position in space, another arrow here in this position of space, and so on, okay? Now, suppose that I want to get the electric flux through a planar surface perpendicular to this electric field vector. This paper represents this imaginary planar surface. So the electric flux is going to be defined in the following way, okay? The electric field through this surface will be defined as being, now the example, let a uniform electric field in the 3D space, okay? Calculate the electric flux of this field through an imaginary planar surface perpendicular to this vector field. Oh, thank you. Okay, now I'm sharing, right? I'm using this example so you can have an idea of the concept of electric flux, okay? We start with the simplest example that you're going to see out there. Let a uniform electric field in the 3D space. Calculate the electric flux of this field through an imaginary planar surface perpendicular to this vector field. Let's see, this surface have sides of lengths A and B, okay? So here you go. Here's A and here's B. That's the dimension of the surface. And because this is an imaginary surface, I'm going to represent that with dashes, okay, like that. Yeah, let's see this one. Dashes, more dashes, more dashes. Okay. Here is the line center that centers the planar surface, the imaginary planar surface. Okay, notice that I put a 90-degree angle between this field and this line that runs parallel to those two sides, to this side, right? And the other side. Because this plane is perpendicular to the lines, we can also define, we do that in physics, an area vector. Okay, the area vector is represented by this red vector. And because I have a red vector, I'm going to also to have red sides here. Here you go. And this center line will be red as well. Okay? Can you picture that? The area vector always points away from the surface. Always points away from the surface. Okay, the electric flux of this electric field through this imaginary surface is going to be defined in the following way, mathematically, right? Solution. 10:46, we are almost there for our break, right? Let me finish that definition first. Is going to be given, the electric flux is represented by, now let's see. Yeah, okay, phi. And we usually put a E, a subscript E, to denote the electric flux. Okay? And it's going to be what? It's going to be given by the electric field itself. It's going to be given by the magnitude of the area. And then it's going to be the cosine of the angle between the two vectors. Okay? And it's going to be like that. Vector E and vector A. That's the definition. Okay, cosine of the angle between E and A, which I'll call, angle phi. That's the definition. Definition of the electric flux. And that, by the way, the same definition applies to other fluxes, to other types of fluxes. Okay, there is also later on, we are going to see that there is also a magnetic flux. Okay, and the magnetic flux is going to be given exactly by the same equation, replacing one field by the other. Okay, and doesn't have to be just electric and magnetic flux, can be other things too. Okay, can be like the flux of particles through a given surface. Okay, flux of the velocity vector of a bunch of particles through a given surface. Okay, and now let's solve this example right in here. Okay, the electric flux, right? The electric flux is given by, right? The magnetic flux is also given by the same equation. Is also given by the similar, is also given by the same equation with the E replaced by the B. Okay? Note that, according to our example, according to the example being illustrated, comma, the imaginary surface is perpendicular to the electric field. According to the example being illustrated. Furthermore, the area vector of this imaginary surface is also perpendicular to this imaginary surface, to the surface. Consequently, comma, the area vector must be parallel or anti-parallel, okay? Or anti-parallel to the electric field. Yeah? So here you go, going back here to our drawings, right? This one right in here. This area vector is perpendicular to the surface. Because the surface is perpendicular to the electric field lines, the area vector is going to be parallel to the electric field lines. Depending how you orient this area vector, it can also be anti-parallel. If it is parallel, it means that the angle between those two vectors is going to be 0. Okay? If the area vector is parallel to the E field, comma, it means that the angle between these two vectors is equal to 0. And the solution of this example becomes the following. Here we go. Zero. Cosine of 0 is 1. And we end up with this following response. The electric flux is going to be E times A. Okay. So that's our first example on electric flux. Can you memorize this equation here? Okay. What I want to do now, I want to take attendance. Any questions before we move forward? Let's see. Cordoba. Okay. Okay, let's see. We have some new students here in the classroom, right? Was Brian Salvador. Okay, so we have Brian Salvador here. No, wait a minute. Yeah, no, Brian Salvador apparently dropped. One more. Here you go. Olivers. Pittman. Straight. Okay, we have. Okay, looks like Candelaria dropped. Yeah, okay. Okay, so let's take attendance now. It's going to be the 24th. Oops. Yeah. Format cell. Date. Okay, so let's start with Abir Ahmad. Are you there, Abir? Yeah, let's see. Edwin, my mic is not working at the moment, but I'm here. Okay, so I can see Abir is in my roster here, but I don't hear from Abir. Okay, gonna put a star here in the name of Abir. Nestor Alvarado. Are you there, Nestor? Looks like Nestor is away the computer. Next is Monte Ambarchian. 24th. Oh, yeah, that's right. Thank you. The 17th was a holiday, right? Delete. Monte is Monte here. I don't see Monte. Yep, there's a holiday. 17. Now let's see. Hasti, Amin, are you there? I don't see Hasti either. Next is Isabella Ballesteros. I don't see Isabella either. Next is Justus. Are you there, Justus? Justus Bowden. No, my goodness. Okay, Alexandra Burmistrova. I didn't hear you, Alexandra, but I saw you turn on your mic, right?
Yeah, I'm here.
Okay, now I hear you. Thank you. Benjamin Carbajal. Carbajal. Okay, thank you. Benjamin Briana Carrillo. Thank you, Briana. Elizabeth Castellano.
Yes, here.
Thank you. Natalia Cordoba. Let's see, I don't see Natalia. Jacqueline Delgadillo. No, I don't see Jacqueline here. Jenny Diaz.
Here.
Thank you. Valerie Diaz.
Here.
Thank you, Valerie. Juan Escalera. Thank you, Juan. Bianca Euloki.
I'm here.
Thank you, Bianca. Dana Gomez.
Here.
Thank you. Edwin Gonzalez. Hello, Edwin. I see Edwin's in my list here, but he's not answering. Ellie Gonzalez.
Here.
Thank you, Ellie.
Edwin said his mic wasn't working.
Okay, who is that?
It's Genesis. He said his mic wasn't working.
Okay.
I think he sent you a message separately.
Yeah. Did I give you attendance? Let's see. Dana, right? Yeah. Okay. Yeah, if I didn't give you attendance, let me know, okay? So any of you. Manuel Hernandez.
I'm here.
Thank you, Manuel. Samantha Hubert. Samantha. Okay, I don't see Samantha here. Faiz Hussein. Okay, I don't see Faiz Hussein either. CJ Joseph Hutton.
Yeah, I'm here.
Okay, thank you, CJ. Luis Leal. Edwin, okay. Edwin, right? So here you go. Thank you, Edwin. Luis Leal, are you there? That doesn't look like. Okay, so I don't see Luis Leal here. Amber, Mary, thank you. Areli, right? Areli Lopez, are you there?
Yes, I am.
Yeah.
I'm here.
Okay.
Yes.
Thank you.
Thank you.
Genesis Lopez.
I'm here. I'm here.
Thank you. Mary Michaelian. Amber Lopez. Let's see. Amber Lopez. Yeah, okay. Mary. Let's see if Mary is here. Hello, Mary. We have a Mary here. Must be her. I'll put a star here. Ramon Oliveris.
Here.
Thank you, Ramon. Taylor Horn. I don't see Taylor. Jeremy Pittman. Jeremy doesn't look like Jeremy is here. Stephanie Ramos.
I'm here.
Thank you, Stephanie. Leslie Rios.
I'm here.
You're there. Okay, thank you. Jason Street.
I'm here.
Thank you. Gemma Torres Navarro.
I'm here.
Thank you. Cindy Vieira. I don't see Cindy. Nuhamin Wandimu. Okay, Nuhamin is not here either. Let's see. Was everybody called? I have 21 here, 22, 23, 24. Abir, I want to give you another opportunity for Abir. Are you there, Abir? Okay, not answering. And Nestor Alvarado. Let's see, I see Nestor here. I don't hear from Nestor. And Mary Michaelian. Okay, I don't hear from Mary. Keep that. Let's go for our break. It's 10:52 right now. 10:52 a.m. We are talking about 11:07, right? 11:07 a.m. break. If you don't have any questions, we can go into the break. Okay, I'll see you in the next 15 minutes. See you. Bye-bye. I'm back here. So that's very straightforward definition, right? Here you go. I can go even further than that. I can write down the area of the imaginary plane is A times B. And that's how we calculate the electric flux. That's the simplest example that you're going to see out there. Although there are more complicated ones, okay? And what do you have to know about Gauss's law? Gauss's law uses this concept of the electric flux. And we are going to do some examples a little bit more involved than what you have seen to solve some very interesting problems, okay? So let's write it down. Gauss's law uses the concept of electric flux, the idea of electric flux. It cannot to solve for the electric field of some charge distributions that are very important, okay? Are very important. And we are going to first formulate Gauss's law, and then we will use it to calculate the electric field, the E field of some charge distributions that cannot be easily calculated. That cannot be easily calculated. Okay, so Nestor is here, right? Let's see, Nestor. Nestor, what's your last name, Nestor? Nestor Alvarado, no? Okay.
Alvarado, yeah, just that my Wi-Fi was down a little bit.
Okay. And Abir, is Abir there? One more chance for Abir.
Yes, I'm here.
Okay, good. So now we have, okay. Now, what do you have to do? You have to memorize Gauss's law, okay? Memorize Gauss's law. Gauss's law. This is a law in physics. Okay? And this is a law in physics. This is a more generic format of Coulomb's law. Coulomb's law. If Coulomb's law applies to point charges only, okay? Gauss's law applies to point charges and plus other charge distributions. Okay? And Gauss's law can be stated in the following way. The electric flux of and I'm going to do that. The electric flux through a closed surface, closed imaginary surface, is going to be equal to, remember that it's going to be equal to 4 pi k, the amount of charge enclosed by the surface. That's how we can formulate Gauss's law. Remember that? The electric flux through, let me just spell that out. The left side is the electric flux through a closed surface in space. And Q enclosed is the amount of electric charge enclosed by this surface. Okay? Like that. 1, 2, 3. like that. Is the amount of electric charge enclosed by this surface. For pi are regular numbers, k is that constant that I have already introduced to you, okay? And now what you're going to do, you're going to come up with some examples. Okay? The first example is that of a point charge. Assume that you do not know, okay? Assume that you don't know Coulomb's law. Coulomb's law, okay? We will use Gauss's law instead. Assume you do not know Coulomb's law, comma. We will use Gauss's law to calculate the E field of the point charge. Okay. Solution. Okay. To calculate the E field, comma, we must calculate the E field using Gauss's law. Comma, we must use a mix of qualitative and quantitative techniques, okay? That's what we have to do. Let's go here, and you also have to come up with a drawing, okay? Let's see. Here you go. Here's my electric charge, point charge, okay? Here's my point charge. I already know that positive charges are sources of electric fields. I already know that, okay? And because this charge is isolated in space, its electric field will look like radial lines coming out from the charge itself. Okay, I'm not using Coulomb's law, I'm just using the fact that those electric charges, those point charges, are sources of electric field. And it's also reasonable to assume that the electric fields, they are radiating away from the charge in the radial direction. That's where the qualitative portion comes about, okay? Maybe qualitative, but it's very powerful, okay? Don't underestimate the power of qualitative thinking, okay? So first step, visualize the electric field emanating from the point charge. And by the way, I'm going to put that first one is that of a point charge from a first find the E field of a positive point charge. When you visualize the electric field, you're going to conclude that the electric fields are radial in the radial direction. Okay, and by the way, I also have to give another piece of information. A point charge, find the electric field of point charge Q, of a positive point charge Q. That's the value of the point charge is Q, okay? Next, second step, build a closed surface around your charge distribution. It cannot be any closed surface, comma, it must be a surface that is symmetric around the charge distribution. Okay, that's the second step. And now the next drawing is right here. Here you go. In order to have a symmetric surface around a point charge, what we must do? We must surround it with a spherical surface centered at the point of the charge. Centered at the point where the charge is located. Okay? So what do you have right here is a spherical surface. For the point charge, it's going to be a spherical surface. Because a point is because a sphere is symmetrical with respect to the point charge. This problem won't be you won't be able to solve this problem if you displace this spherical surface like that. You won't be able to solve this problem because it becomes too difficult. Okay. However, if you center it right where the point charge is located, it's going to be easier to solve the problem. Why is it going to be easier to solve the problem? There's a reason. There's a reason for that. Remember that the flux is dependent on the angle between the electric field and also the surface vector. Okay? Remember that, right? Note C that the electric field right here at this point is normal to this spherical surface. Do you notice that? And we have the same angle right here too. It's normal at this point here. The electric field is going to be normal to the surface at this point everywhere. If you displace the surface, you won't no longer have the same angle between the electric field lines and the normal to the surface. This angle is going to vary throughout the whole surface. It's going to become almost impossible for you to solve this problem. Okay? For this reason that you have to choose a proper surface and second, locate it properly as well. Okay? And I'm going to also to mention something very important. Gauss's law doesn't solve every problem out there, okay? Let me put that here. A caution, right? A word of caution. Gauss's law does not solve every problem. It solves some problems that have symmetry, like the one of the point charge. Okay. Now that I came up with a surface, right, that symmetric with respect to the point charge, here you go. I can go ahead and elaborate here. Here you go. We are going to have an electric field right in here. We're going to have another electric field that is going to be pointing in this direction. Perpendicular, normal, right? Not perpendicular, but normal to the point charge, to the surface. Normal to the surface enclosing the point charge. Here you go, right here. But there is one more important piece of information. Because the distance of this point charge to this point is the same as the distance of this point charge to this other point, it means that your electric field at the magnitude of the electric field at this position is going to be the same as the magnitude of the electric field at this other position. Okay? So we can, here you go. Third step. Third step. Recognize that the electric fields at the imaginary surface, at the imaginary spherical surface, at the surface of at the surface of the imaginary sphere, okay, comma, are at the same distance from the charge. For this reason, we can state that the magnitude of the electric field throughout this whole surface is the same. Okay, that's another important piece of information. Okay, so that's exactly what I put it here. The electric field here at this point is going to be this, they have the same magnitude at this point, the same magnitude at this point, and so on, okay? And that's a very important piece of information as well. On the top of that, the area vector is going to be parallel to the electric field. The area vector is this red arrow, see that? Exactly because of the symmetry of the surface that I choose. Fourth step. Recognize that the area vector is parallel to the E field. Area vector of this imaginary surface is parallel to the E field. And now we are getting there, right? We can start using our equations. I'm going to use the equation for the flux of the electric field. Okay, the angle between the area vector and the electric field vector is going to be 0. Consequently, the electric flux is going to be EA. And by the way, I'm going also to say that this surface here is a distance r, lowercase r, from the center of the charge. Okay, so let's see. I'm going to get, here is going to be lowercase r, like that, lowercase minus r, lowercase minus r. That's the radius of my imaginary surface. Lowercase plus r. Like that. And now that we came up with a given distance, right, from the center, we can here write this equation that you see right in here as the area of a sphere. The area of a sphere is 4 pi r squared, okay? Right now, we're just looking at the left side of the equation, right? Right now, we're just looking at this left side of the equation. I still didn't worry about this other term on the right side, okay? Here you go. I'm gonna copy and paste right in here, okay? That's what I got. Can I do better than that? Doesn't look like we can do any better than that. We went as far as we could. We want to calculate this guy right in here. That's the one we want to calculate using the Gauss's law. So what we have to do now, we have to use the right side of the equation. We use the left side of the equation. Let's use the right side now, right? 4 pi k, Q enclosed. I told you that the charge that we are calculating has a magnitude Q, and this charge is completely enclosed by my imaginary surface. So this Q enclosed is going to be exactly equal to Q. And now I can start solving my problem. We know, we know Q, we know K. And if we solve our equation, we are going to find out how the electric field changes with the distance, okay? So here you go. I'm gonna put this term right in here on this left side. And now look what we can do. We can solve this equation for E. This is a nice technique that people discover, scientists discovered, right? 4 pi cancels with 4 pi. And then we finally have E equal to KQ squared. Okay. Think about that. Just a little 2-3 minutes pause, right? Think about that, how you solve this problem. And then I'm going to show you other problems as well that we can solve using this technique. Okay, so here you go. That's one example. Now let's look at another example. Using the same technique, 1130, we can go for another example. Next, we use Gauss's law to find the electric field of the uniformly charged thin spherical shell. A spherical shell uniformly charged. Let's put it this way. The electric field of a spherical shell uniformly charged of radius r, okay, and charge q. The first thing that you have to do is to illustrate this spherical shell. That's the point charge. Okay, let's. By the way, Gauss's law cannot be used to solve this type of problem on positive and on another negative charge, okay? Because there is no symmetry here in this case. It would be almost impossible to solve using Gauss's law. Point charge. Go point charge. Point charge. Okay, spherical shell. Here's the spherical shell. It is uniformly charged. Has a charge Q, a radius R. Okay. And now you have, the first thing you have to do is to figure out which surface is going to be symmetrical with respect to this spherical distribution of charge, okay? If we use a spherical surface as an imaginary surface for the point charge, what should we expect to use for this spherical shell? It's rather straightforward, right? If you have a spherical shell, we are going to use a spherical imaginary surface as well. And here you go. We are going to start for a place, for a region that's less than the radius of the sphere, of the spherical shell. We're going to start with this surface right in here. Okay. Okay, start with r, lowercase r, less than uppercase r, inside the spherical shell. So we go ahead, we apply the left side of Gauss's law, right? That was going to be the flux, EA cosine of phi. But wait a minute. We do not have any charge inside that spherical shell. The amount of charge enclosed by this by this imaginary surface is 0. Okay? So we go ahead and write down that this term here that you have right here must be equal to 0. The area of the surface is not 0. Cosine of phi is not necessarily 0. Consequently, the only thing that can be 0 is going to be the electric field. Okay? The only thing that's going to be 0 is the electric field. And then we conclude that inside the sphere, the electric field is equal to 0. Now, what we're going to do? Now we're going to do the same thing, but for a region of the sphere that's greater than R. Okay? And we do exactly what we did for the point charge. The point charge is just like a very small sphere, right? Here you go. That's the radius of the imaginary surface, okay? And since there is no charge there inside, the electric field must be 0. Now let's go outside the sphere. Here you go. Here's the spherical imaginary surface enclosing my spherical shell. We do know that the spherical shell must have electric fields that are radial in the direction, just like for the point charge. We must have something like that. And you can play just the way I did before, right? What would be the electric field contribution to this point charge right in here at this, let's say at this spot, right? The electric field contribution of this point charge is going to be something like that. But then this other electric field is going to cancel out the contributions that are in the tangential direction. And we can conclude that the electric field is going to be perpendicular to this imaginary surface everywhere. Okay? And now, let's go. We have, here you go. All I have to do is to copy what I had before. Here you go. Okay. The electric field, okay, EA is going to be, EA cosine of phi is going to be EA. The area is going to be 4 pi r squared. And then we are going to have 4 pi k BQ. BQ stands for the electric charge on the surface of the spherical shell. BQ here, BQ here, and BQ here. Very similar. And then we can state that the electric field for a spherical surface is going to be given by this equation. Oh, no, not this one. This other one here. Here you go. Zero for r less than big R, Q over r squared for r greater or equal than R. Okay. And now we are going to calculate the electric field of a planar distribution of electric charges. Remember that I told you a planar distribution of electric charges had a uniform electric field? Well, we are going to find that out right now using Gauss's law. Find the electric field of a very large flat plate of uniform charge distribution. Okay, no need, you can write it down. No need to worry about edge effects. Effects at the edge. And we're going to need our drawings, just like before. Let's see. That's another example. I'm not going to do it. Okay. This is other example. I'm not going to do it. I'm going to do, let's see. Uniformly charged cylindrical shell. No, not this one. Okay. That's this one here. No. Okay, right in here. Gauss law, infinitely large planar surface. Okay. So here you go. My infinitely large planar surface. If we apply that idea that I told you before, right? The electric field at this point is going to be the electric field contributions of each charge separately. And then you go ahead and sum them up. When you do something like that, you come to the conclusion that the electric field must be pointing away from this planar distribution of charges, and it is going to be in the horizontal direction because this planar distribution of charges is very large. Okay, so let's do this step by step. First step. On the planar surface, right? First step. And by the way, net charge Q greater than A, greater than 0. To calculate the field using Gauss's law, we must use a mix of qualitative and quantitative techniques. First step, visualize the electric field emanating from the planar surface. Okay. And then second step, because the flat surface, the planar surface is very large, planar surface is very large, comma, it's reasonable to assume that the electric field will be perpendicular to the planar surface. Okay? And that's what I did here. That's what I did right in here, right? Get a point anywhere in the space, you will recognize that the electric field is going to be kind of perpendicular to this surface. Okay? In the next step, you go ahead, you build a cylindrical surface that encloses a given amount of charge. The cylindrical surface is symmetric with respect to this planar distribution, okay? And, okay, next step. Third step. Build a closed surface around your charge sum, or let's say sum of your charge distribution. It doesn't have to be all the charge distribution, okay? Sum of your charge distribution. It cannot be any closed surface. It must be a surface that's symmetric around the charge distribution. For the planar charge distribution, this imaginary surface must be a cylinder. Okay? Must be a cylinder. This cylinder is formed by 3 different surfaces. The 2 caps at the extreme of the cylinder, and the side surface of the cylinder. Okay, so going back here we go. We have surface number 1, surface number 2, and then surface number 3. See that? Surface number one is the cap on the right side. Surface number 2 is the cap on the left side. And surface number 3 is the side surface of the cylinder. Okay? Recognize that the E fields at the surface of the margin are at the same, let's see. Build a closed surface around the sum of your charge distribution. Cannot be any closed surface. It must be a surface that's symmetric around the charge distribution. For the planar charge distribution, this must be a cylinder. Okay. Fourth step, right? Fourth step. Recognize that this cylinder is formed by 3 different surfaces. The 2 caps, surfaces 1 and 2, surfaces 1 and 2. The 2 caps at the extreme of the cylinder, surface 1 and 2, and the side surface of the cylinder, surface number 3. Okay. Fifth step. Fifth step. Document the directions of the vector area of each surface. Okay. So we have 3 surfaces. We must have at most 3 vector area. The vector area of this first cap must be away from the center of the cylinder. That's how we usually do. We always choose a direction that is away from the solid, okay? Not towards the center of the solid. This other cap here is going to have an area vector that's going to be to the left. This one's to the right, this one's to the left. And finally, we are going to have this other surface area and vector surface, vector area, right? That's going to be upwards, okay? And now you have to worry about the flux through each of those surfaces. And that's what's going to be the next step, sixth step. Sixth step. Calculate the flux through each surface. Okay, the electric flux through each surface. So it's going to be electric flux. It's going to be like that. The total electric flux, right? The total electric flux. Calculate the total electric flux through each of the surfaces. So it's going to be, you know, flux through the surface number 1, flux through the surface number 2, flux through the surface number 3. Okay. We do know that, here you go, we already know that the electric field points to the right in this region here, and the electric field points to the left in this region here. So when we multiply EA cosine of the angle between them, since the angle is going to be 0 degrees, right? Both on the left side and on the right side, we are going to get, you know, the electric field on the right surface is going to be EA plus the electric field on the left surface is going to be E2, right? E1A, E2A. And the area here is going to be exactly the same as the area here. And then we have the flux from the third surface. The flux from the third surface must be 0 because the electric field makes an angle of 90 degrees with the area vector. Okay? The electric flux through this surface is going to be 0. So, plus 0. And then we are going to have our right side, the right side of the equation, right? The right side of the equation. Don't forget this uniform charge distribution. Let's see here. Uniform charge distribution. Now we are going to calculate this value right in here. We do know that the net, there are several steps. Do you notice that? There are several steps. We do know that the net charge divided by the total area. And by the way, here I should put A prime, okay? So I do not mix up with the net area of the plate. Here you go. Area A, see that? I should use A prime. A prime is less than A. Okay, so since it's, is uniform charge distribution, it means that the amount of charge divided by the area is going to be given by this charge, what we call charge density. Okay, and this charge density is also going to be given by Q enclosed. Very soon we're going to start our break, okay, divided by A prime. Hey, what the heck happened here? Okay, now we got it like that. If we want to find Q enclosed, all we have to do is to solve for Q enclosed. Okay, and we get, Q enclosed is A prime divided by A times big Q. Like that. Even better, I'm going to put a big Q here outside this ratio so you can visualize better the equation. Like that. One more thing. Right? Let's replace, here you go. Let's write that down. Let's see, we want to use this equality right in here. Q enclosed. Place right in here. Something neat happens. It happens with rather frequency in physics, okay? Notice that we have A prime here, A prime here, and A prime, oops, and oh no, boldface that I want, and A prime here, right? So that means what? It means that we can cancel something that we do not know the value of, okay? We still do not know E1 and E2, but we can come up with a very important step, okay? Making this distance here equal to this distance is very reasonable to state the electric field here, the magnitude of the electric field here will be equal to the magnitude of electric field here, okay? keeping both caps at the same distance from the planar charge distribution, comma, it is very reasonable to state that E1 is equal to E2. E1 is equal to E2, which, by the way, is going to be given by E. Okay? And now we are almost there. We are almost there. E1 equal to E2. E2 is equal to E1, let's say, right? Here you go. I'm gonna put E. E1 equal to E, E2 equal to E. It becomes 2E. And now we solve the problem. These two cancel out with the 4. And then what we get? 2 pi k q over A. Okay, that's what we get for the electric field of a planar distribution of charges. Okay, because the above solution does not depend on the distance from the planar distribution, comma, then we may state that the field is uniform, okay? It's uniform. That's the technique that I want you to work with, okay? Right now we know we proved that the electric field is uniform. Not only we proved that the electric field is uniform, we also show that the electric field is given by this equation here, 2 pi k q over A. Okay. And let's take a break now. Any questions? Okay, break. 11:57 a.m. to 12 a.m. p.m. So I see you in 15 minutes. I'm back here. And we're done with chapter 2, right? The only thing that I want to tell you is, what we did, the solution above. The above solution is for a single planar surface. For a single planar surface. When you have two planar surfaces facing each other, and separated by when you have two planar surfaces, one positive and the other negative, face each other and separated by a given distance, then all you have to do is to use the superposition principle. Okay, so I can illustrate that. This one is very straightforward. Here you go. That's what we have here, the positive plate, right? You already know what's the value of this field. 2 pi k q over a. Okay? This one too. If you have a negative field, you also know the magnitude of this electric field, which is also 2 pi k q over a, right? You superimpose those two plates, and now what's going to happen? The net field is going to be the sum of the other two here in the inside. In the outside, it's going to be 0, okay? So there were solutions for a single planar surface. When you have two planar surfaces, one positive, one positively charged, and the other negatively charged, face each other and separated by given distance, then all you have to do is to use the superposition principle to find the net electric field. Okay? So what you're going to get is between the plates, the net field is going to be one plus the other, or twice what you had before, 4 pi k. That's one way of, outside the volume between the plates, E field is equal to 0. Okay? And then you can repeat also for two positive plates, two negatively charged plates. We can use the same principle for those other two configurations, okay? And there is another way of expressing, this value here. There is what we call the dielectric constant, okay? This, this result can also be rewritten in terms of another parameter we call the dielectric constant, epsilon naught. And there is a relationship between K and the dielectric constant when we use, and it's going to be like that. Sigma here is Q over A, okay? I'm going to 1. Where sigma, yeah, there is a relationship between epsilon naught and K, and well, that's what you end up getting. Here you go. I can write down the relationship. The relationship between epsilon naught and K is like that. Okay. Oh, wait a minute. That's not between the two plates. It's supposed to be 4 pi K here. Yeah, 4 pi K. Like that. Let me see one thing here. No, wait a minute. There's something wrong here. It's like that. It's more like that. Yeah, it is. Yeah, that's right. It's like that. That's the relationship between them. So what you end up having here is going to be like that. 1 epsilon 4 pi K, 1 over epsilon naught. Okay. There's no 2 here. 1 over epsilon naught. Let me check here. There's a sorry for the confusion. There's a relationship between dielectric constant and K. Let's see. No, that's not what it is. You know, stick just to the K. I'll get back to you later on. Okay, let's erase that. You know, that's I'll get back to you later on the relationship between epsilon naught and K. Let's just stay this way here. And we can also take a look at the book. Two plates facing each other. Sigma over epsilon naught. Yeah, okay. Sigma over epsilon naught. And so yeah, so epsilon naught is given by that equation that I told you. So epsilon naught is indeed one over epsilon naught okay. Epsilon naught is equal to that. Is equal to that. And now we have the field written in terms of epsilon naught A. Not this one. This one here that I want to erase it. Here you go. Either way is correct. In your book, this ratio here that you see, we display as sigma. We call it sigma, okay? Which is the surface charge density. I'm going to put this epsilon naught as the ratio so I can have it. Here you go. Calling this sigma. Okay, and we get the result from the book. If it is just one planar surface, the field will be half of the above value. But don't forget, outside this region, the electric field is going to be 0. That's what we have, okay, right in here. And yeah, positive and negative plates. Okay, so that's what we have for this chapter. We have 30 more minutes to go. I want to start the next chapter, which is electric potential energy and electric potential. And by the way, when you in real life, okay, electric field is a very important concept. However, electric field is a very important concept. However, there's a problem with the electric field. It is very difficult to measure, right? With instrumentation. Very difficult to measure with instrumentation. Instead, we usually measure something else. We usually measure something else that is related to the electric field. This something else is called electric potential. Okay? This something else is called electric potential. Is what is measured, is measured in volts, which is measured in volts, abbreviated by the letter V. Okay, so let's just summarize what we have done so far, right? I like to keep track of those things so you know where one thing comes from, when those things come, where they come from, okay? Skipping 5, 6, 7, yeah. 8. Then let's take a look right in here. My list of things, of concepts that we started working on. Well, I don't need to do that. I can recall that from heart, by heart. Let's do that. Okay, so we started with electric charge. Then I introduce you to the electric force, Coulomb's law. Coulomb's law. Then the electric field. Okay. And then now I'm going to introduce something else called not the electric potential, but the electric potential energy. Okay. Remember that electric gravitational potential energy or potential energy? We had that in physics 6, right? And then after the electric potential, now we have what we call the electric potential. Okay? There is no counterpart of the electric potential in mechanics. By mechanics, I mean physics 6. Okay. Yeah, let's see. I'll get this thing. I want to save some space here. Yeah. Electric potential. There is no counterpart. It has no counterpart in mechanics. The electric potential has no counterpart, but it does have a counterpart. But the other one has this one, potential energy is its counterpart in physics 6. Okay? It's much easier. It is much easier to measure the electric potential. So much that they sell $10 devices that are capable of performing this type of measurement. And let's see how we are going to define that, okay? Strictly define that. We start with the gravitational field nearby the Earth's surface. And let's see if I can get a table here. Yeah, I have a table here. I'll show you the table later on, okay? So start with electric potential energy, versus gravitational potential energy. Okay, that's what we call potential energy, or just potential energy. Remember that? We start with the gravitational field nearby the Earth's surface. We have gravitational field nearby the Earth's surface, gravitational force. I'm gonna take out the vectors to make things simpler, okay? It's just mg, right? But then later on, you learned that for these specific case, we also have a potential energy associated with it, right? And the potential energy that we have associated with it, I'm going to specifically state, is the gravitational potential energy, when I'm going to put the G down there so you can remember that. Strictly speaking, it's not the gravitational potential energy, but it's something else that we call the difference in potential energy, the gravitational difference in potential energy. Okay, so here you go. Gravitational potential energy, gravitational force, and gravitational potential energy, right? But then later on, okay, let's do something else. The higher the mass is above the Earth's surface, right? The greater its potential energy. But then later on, you learned that there is a more exact relation for the gravitational force. You learned, according to, Newton's law of universal gravitation, that this gravitational force is not exactly mg. It actually changes as you move away from the Earth's surface. Okay, so what you see here is just an approximation to what you see right here. This equation is a more exact, is an exact relation for the gravitational force, okay? Relation for the gravitational force. And then, if you remember from physics 6, the gravitational potential energy associated with this force is going to be what? It's going to be minus GMM divided by R. Okay? It's not difficult to memorize, right? If the mass is infinitely distant, okay? If the mass is infinitely distant, then this potential energy is going to be 0. Okay, we have the same thing. We have something similar for electric charges. Okay? For point charge, we already saw that the electric force is what? I'm going to put E here for the electric field. It's going to be K. I'm going to put big Q, big small q, divided by R squared. Consequently, taking the gravitational potential energy as a guide, right? The electric potential energy is going to be quite similar in its format. Or I'm going to give you the exact value. And don't forget this one here is the gravitational potential energy. I'm putting a G in there. Here I also have to put a G here too. This guy is an approximation to the other one, right? We can also figure out that the electric potential energy is going to be a similar equation, but doesn't have, with the only difference that doesn't have this negative sign. And also, we must have the masses replaced by the charge and the big G replaced by the constant K, okay? Where does it come from? Where does this definition comes from? It comes from the idea of work done by a force, okay? That's where it comes from. So if we're going to, so we can go ahead and build our table. That relates one with the other, right? Here you go. Again, I'm going to remove the vector, the vectorial constant there. This negative means that the force is attractive, is always attractive. Important difference between the electric force and gravitational force, right? If this one has a negative value here, this one must have a positive value. Any attractive electric force must have electric charges that are opposites in sign, okay? And because of the fact that we do not have negative masses in the universe, right? We still get a negative sign here, but a positive sign. And the electric potential energy is going to be negative only when one charge is positive and the other is negative. Okay? That's for a point charge. The above result apply to point charges and point masses. Okay? But note that notice that for the case of a uniform electric field, comma, this should be related to the gravitational force nearby the Earth's surface, right? I'm talking about this one here, nearby the Earth's surface. The gravitational force is just mg. What does it mean? It means that the gravitational field is uniform. Okay? So we do also have a counterpart for this specific case. Okay? The counterpart of the above one, the electric counterpart of the above case is that of a uniform electric field. Okay? So, if for the gravitational force, so let's go. We're gonna repeat it here. Exactly the way I repeated the other. Gravitational force, electric force. If for the gravitational force we have mg, for the electric force, we are going to have Q times E. Okay? Remember I told you before that the acceleration of gravity is in reality the gravitational field, what we also call the gravitational field. And because of that, you know, we also have the electric potential energy for the case of a uniform electric field, which is going to be Q, E times X, if the electric field is in the X direction. If the electric field is in the X direction, okay? And by the way, if here I have a positive sign, here I have a negative sign. Okay? Because like charges repel, okay? Repel each other. And now we can build a more complete table that includes our uniform electric field. 10 more minutes to go. Okay, so here you go. Gravitational force is mg, electric force is going to be QE. Uniform field, let me emphasize here, uniform field, right? Gravitational force, they have almost the same format. Gravitational force, electric force for a point charge. I put point source, right? Point source because here the mass is the gravitational source, whereas the charge is the electric counterpart for the source. And now that we have potential energy, we can define something else that we call electric potential. Okay, so we have the electric potential energy in addition to that, which is similar to the gravitational potential energy. In addition to the electric potential energy, we also have the electric potential, okay? Which is different from the electric potential energy. And how do they differ? Okay, how do they differ? All you have to do, how do they differ? How do they differ? All you have to do is to divide the potential energy by the electric charge. Okay? And if so if the electric potential energy EP is okay, comma, then the electric potential of a charge distribution Q of a point charge. Let's put if the electric potential EP of a point charge, I gotta put here point charge, is given by that, the electric potential of a point charge of a point charge Q will be given by, here you go. Now, because we have a different quantity now, I will write down, instead of U, I'm going to write it down in terms of V. And this Q, little q disappear. Okay? Although you didn't study you didn't study gravitational potential, we may define gravitational potential here in this course as well. Okay? For a uniform electric field, okay, for uniform electric field, we have the electric potential energy is electric potential energy uniform, this one here, minus QEX, right? Is and let's see how we're going to define electric potential. Okay, that's going to be U. And let's put that E here, so you know it's related to an electric quantity. I'm going to put it, doesn't have to be, and I'm going to put, yeah, like that. And this one, I want a black color as well. Consequently, the electric potential, what's going to be the electric potential? EP is going to be this value that you see right in here. Divided by Q, and I'm gonna put V. Okay? And there's just gonna be EX. And now I can come up with the table, with a better organized table. It's gonna look just like that. Here you go. Force, field, potential, energy, potential, just potential. Gravitational force for a uniform field is mg. Electrical force for a uniform field is QE. the gravitational field is going to be just the acceleration of gravity, and the electric field is going to be the force divided by the charge. Notice that here too we have force divided by the source, right? By the mass. If here we have force divided by the mass, here we have the force divided by the charge. Gravitational potential energy mgy, electrical potential energy is minus QEX. Q is the source of the force. Q and M are the sources of the force, of their respective forces. G and E are their respective fields. And here are the coordinates from a given position. And the potential, the electric potential and the gravitational potential, we can define a gravitational potential as well. It's just their respective potential energies divided by the source. The source of gravitational force is going to be the mass. The source for the electric force is going to be the electric charge. Okay? That's for the uniform field, and here is for the point source. Okay, it's 12:49 there right now, and what we do use in physics in most measurements is this type of idea here, is this concept that you see right in here, is the potential. It's much easier to measure the potential than to measure the electric potential than to measure the electric potential energy, okay? And that's what we are doing in this lab 1 and 2. So I'm gonna stop right now. Has been a long day, right? Lots of ideas, lots of definitions, but you have your gravitational counterpart to start becoming familiar with those formulas. Okay, so I see you again on Wednesday, and I'm gonna have my office hours right now. See you. Okay, pause, stop, break, stop record.